We're reviewing continuity and also differentiability. Is this piecewise function differentiable at x equals 0? Show all work that leads to your answer. Well, let's first check to see if it's even continuous at x equals 0 at the break. Because if it's not continuous, there's no sense in checking for differentiability. So to check for continuity, it's a three-part continuity test. Part 1, is the function defined at the x value of the break? Well, 0 belongs to this bottom piece. So everywhere I see x, I'm going to replace it with 0. Yep, so the function is defined. Step 2, does the limit exist? Well, that requires us checking the left limit and the right limit. If I'm approaching 0 from the left, I'm on the top piece. So everywhere I see x, replace it with 0. So that becomes e to the 0, which is 1. All right, let's check the right limit at the break of x equals 0. As I approach 0 from the right, I'm on x squared plus 4x. Everywhere I see x, replace it with 0. And I end up with 0. Well, we can see that the left limit does not equal the right limit. 1 does not equal 0. So it's not even continuous. It looks like there's going to be a jump discontinuity there. All right, so from both of these, we can say, therefore, the limit as x approaches 0 of the function does not exist. Okay, so I've shown all my work, but I'm also going to wrap it up here and say that f is not continuous nor differentiable. At x equals 0. Question 2, consider this piecewise function. Is f of x continuous at x equals 2? Show all your work. So three-part continuity test. Okay, the break occurs at x equals 2. 2 actually belongs to the top piece, so everywhere you see x, replace in 2. Uh, 3 times 4 is 12. 12 minus 2 is 10. All right, part 2 of the continuity test says consider if the limit exists. So as I approach 2 from the left, I'm on the top piece. Plug in 2. Well, I'm going to get 10. Evaluate the right-hand limit. Plug in 2. That's also going to result in 10. All right, so from this I can say, therefore, the limit as x approaches 2 equals 2. The limit as x approaches 2 of the function equals 10. All right, so moving on to the third part of the three-part continuity test. The third part says, okay, does your functional value equal your limit? Well, yeah, it does. F of 2, which is also 10, is equal to the limit as I approach 2. So the point itself at x equals 2 is equal to the limit as you approach 2. So therefore, f is continuous at x equals 2. Part B of this question, is the function differentiable at x equals 2? All right, so we're going to have to figure out the left slope and the right slope. Okay, here's some way to show your work. Left slope, totally acceptable. All right. So what's the limit as x approaches 2 from the left? Okay, so go back up to the piecewise function. That's going to be this top piece. Find the derivative. Differentiate the top piece and get 6x. Okay, now plug in 2. So the slope from the left is 12. It's pretty steep. That parabola must be pretty steep at x equals 2. Let's find the right slope. So the limit as x approaches 2 from the right. That would mean we're on this linear piece. That derivative is 2. Now plug in the 2. Well, that's going to give me a 2. No, the parabola ends pretty steeply, but the linear function not so much. These two values are not the same. So I'm going to say, therefore, the limit as x approaches 2 of the derivative f prime of x does not exist. Because that's what these were. Each of these expressions right here were the derivatives. Okay, so the limit of the derivatives as x approaches 2 does not exist. All right, let's find the average value from 0 to 6 of the function. All right, so to find the average value, 1 over b minus a, we're dealing with the piecewise function. So we've seen something kind of similar to this in the past, in the pretty recent past. All right, I had to take a look at those functions again. Okay, not a lot of room, so I'll try and write small. I'm going to write all the way across and then continue down. So 1/6. Okay, we're going to have to break up the function into its representative pieces. So the first piece goes from what, 0 to 2. That's 1/6 of, I need to find the area from 0 to 2 of 3x squared minus 2. Plus, I need to add that to the area from 2 to 6 of the linear piece 2x plus 6. So not altogether difficult, just a lot of tedious calculations. Okay, let's find the antiderivative. X cubed minus 2x, we're going to evaluate that from 0 to 2. Plus antiderivative x squared plus 6x, evaluated from 2 to 6. All right, let's plug in 2. So that's 2 cubed 8. 8 minus 2 times 2. So let me just write that down. 2 cubed minus 4 minus, plug 0 in, nice, that's 0. All that's from the first antiderivative, plus x squared, 36 plus, put in 6, 36 again, minus plug in 2, 4 plus 12. Eight minus 4 is 4. 4 plus 72 minus 16. $76 minus 16 is 60. So I arrived at an answer of 10. All right, so now we have another piecewise function. It actually has 3 pieces, and we're supposed to find A, B, and C so that the function is continuous and differentiable on the interval from -3 to 4. So kind of paying attention to this piecewise function, we see the first piece is linear from -3 to 1. So we've got like a line segment. And then the second piece starts at 1 and ends at 4, but it's a cube. And then the third piece is actually a point. The point 1, -1. All right, so let's find A, B, and C so that G is continuous and differentiable. So the first thing we're going to check is for continuity. Okay, and remember what we do for continuity is we just plug in the x value of the break, which is x equals 1. We just plug we plug x equals 1 into each of the pieces and see if we get the same value. So continuity deals with the function itself, the actual pieces. All right, So I'm looking at the limit as x approaches 1 from the left of ax plus b, a plus b. Great, I don't have a number. The right-hand limit, cx cubed minus 3. Plug in 1, and we're going to get c minus 3. Okay, if it's going to be continuous, then these two have to be equal. All right, and sometimes you kind of look out when you set them equal, things can solve, but notice how you have 3 unknowns in one equation. Well, we're not going anywhere quick with that. But also remember, take a look back at that piecewise function. Also remember that a plus b must equal -1 because that is the y value at 1. So if this piecewise function is going to be continuous, it has to be that the limit equals the y value. All right, so we have this statement. So 2 unknowns, 1 equation, a little better. Okay, also, c minus 3 must equal 1, -1. Well, that's nice. I can add the 3 and say that c is 2. Now that I have c is 2, I can plug it in back here, okay, but I still can't find a and b yet. Okay? And it's not going to be until we set up the differentiability piece that we're going to be able to actually solve for a and b. All right, now it's time to turn our attention to differentiability, and what we're going to be looking at is the derivative of each of the pieces. So we're going to find the derivative, plug in x equals 1 to both derivatives, set them equal, see what happens. So as x approaches 1 from the left, we're on this top piece, this linear piece. Well, the derivative is going to be a. So just plug in 1 and we're going to get a. The left slope is a. As I approach 1 from the right, I'm on the second piece, so find the derivative. Power rule, 3cx squared. Plug in 1 for x, you're going to get 3c. All right, well, from that, if we want the function to be differentiable, we have to have the left slope equal the right slope. So a must equal 3c. Oh, that works for us. We know what c is, so let's put that in there and get a. Now that I have a and c, I can find b. So going back to a plus b equals -1. Back here. Okay, if a is 6 plus b equals -1, subtract a 6, b is -7. All right, so you just want to do continuity and differentiability and set the, find the y values at which the functions agree, find the y values at which the derivatives agree, and then you can back your way out of the problem.